Okay, this will be the recording that I promised to you, and this will be most of 6.5, trigonometric form of a complex number. So here's my plan. I still have to finish a little bit on 6.4. I'm going to do that on Monday. And then we'll finish up this 6.5 either Monday and or Tuesday. If you want a recording outside of class, I can work on that as well. And then Wednesday, we'll have a morning class for the review of the test, and then and Wednesday in class we'll take part 1 of 6.1 to 6.5 exam, and then no class on Thursday, excuse me, and then Friday we'll take part 2 of that test. And I will uh, I will put this recording of the first part of 6.5. It's going to be most of 6.5 on my Yola site, and I will send it in an email, and I will try to attach it to the email if I can. I'm not sure if I can do that, but I will also attach to the email the review problems for this section. And so I'll try to not go into super detail on some of the things that I usually do. So this is trigonometric form of a complex number, 6.5, and we're going to plot complex numbers in the complex plane and find absolute values of complex numbers. Write the trigonometric forms of complex numbers, multiply and divide complex numbers written in trigonometric form, use de Moivre's theorem to find complex or powers of complex numbers. And so all of those we're going to cover right now. There is one more objective, find the nth roots of complex numbers, and we'll save that for in class either on Monday or Tuesday. First, we're going to talk about the complex plane. It's not super difficult if you just think about a coordinate axis, but now the x-axis will be the real axis, and the y-axis will be the imaginary axis. Imaginary axis. And so I'll go to this next slide that shows a nice little picture of that. Now we're talking about I, which is the square root of -1. And so if we have z equals a plus bi, we can represent that in a complex plane as a coordinate pair a, b. And so then I have a couple of, I tried to leave up some of my old note things so I could go just a little faster. So if I have a complex form like this -2 minus I, that's like -2 minus 1I. So the coordinates would be -2, -1, and then that's this point right down here. And so the x-axis again is the real axis, and the y-axis is now the imaginary axis. So we just plot a point like we ordinarily would. And then we'll just move right along. And this is now the definition of the absolute value of a complex number. And so it's the distance between the origin and that point AB. So you pause this as you need to make notes and things like that. I will just read through this definition and just expect that you're writing something. So the definition of the absolute value of a complex number, the absolute value of a complex number, z equals a plus bi, is the absolute value of z, which equals the absolute value of a plus bi, which equals the square root of a squared plus b squared. And so that is going to give us, again, the distance from the origin to that point AB that we have on that complex for that complex number, excuse me, as we look at that. And so then we're going to do a problem where we're going to put that in the complex plane. And if you have graph paper handy, that would be great. Otherwise, doing this on notebook paper shouldn't be bad either. And so this says plot z, which is -2 plus 5i. And we're going to plot that as a point and then find its absolute value. So remember, z equals a plus bi. That means a is -2, b is 5, and so our point that we're going to plot is -2, 5. And when I plot this on this axis, -2, 1, 2, 3, 4, 5, that point would be right there as -2, 5. And then that absolute value, and I'll write that in yellow and then get rid of it, the absolute value is the distance from that origin to this point that we have there. And so it's the distance formula, the Pythagorean theorem, all that good stuff. And so the way we'll write that is the absolute value of z equals the square root of -2 squared plus 5 squared, square root of 4 plus 25. So the absolute value of z is equal to the square root of 29. Of course, if needed, we would put that in simple radical form. So I'll just kind of leave that for you to remember as you go through things. So graphing in the complex plane, pretty easy. Absolute value of a complex number in complex form, pretty easy too. Next is trigonometric form of a complex number. And I will go to this slide, but I'm going to kind of just remind you of these things from before. And so if we have a point like 3, 4 over here, and we plot that on the coordinate axis, and it's in that first quadrant, I think that's easier to see. Then along the x-axis, we're going 3. In the y, we're going 4. Remember, we can get that 5 as the square root of 3 squared plus 4 squared. I picked an easy 3, 4, 5 triangle, so that's the square root of 9 plus 16, square root of 25, which is 5. And so that's that r that we've had before. And so we have our x value, our y value, and our r value. That's supposed to be r, a little hard to see there. And so then we know that the sine of theta is y over r. And so I'm going to just rewrite that as the sine of theta is y over r. And so r sine theta is equal to y. And so that's going to be right there. And then likewise, the cosine of theta, just by the picture, is 3 over 5, or x over r. This is kind of a review of earlier work. So that means r cosine theta is equal to x. And so then that transfers over to here. And we know from earlier work that coordinates of that point can be considered r cosine theta and r sine theta. And so let me get rid of all that yellow if I can. And so that's what I just want to go through and remind you as we do this. Now, I intentionally picked something in the first quadrant, and so if my point was in some other quadrant, this angle right here is the reference angle. So I just want to be aware of that. And so also remember that tangent of theta, if we go back over to this one that we were just talking about, the tangent of theta is y over x, and we can use that to find the angle, but that's the other part where I want to say if this is over here, then oops. Then this theta that we would get would be the reference angle, and then we'd have to figure out that angle using kind of the all students take calculus. So trigonometric form of a complex number is just going to take this a plus bi that we've just were talking about a few minutes ago, and this just is in a different quadrant. I like to look at that in that first quadrant right now, but the same thing. So we were calling them x and y before, but now we can call them a and b because they're in the complex plane. And we're using that a plus bi format. And so then because that xy version from before we knew was equal to r cosine theta and r sine theta, we can say the same thing holds now with this a and b in the complex plane. And so that also means that r is going to be the square root of a squared plus b squared. And so then we can get the trigonometric form of a complex number where a plus bi is equal to r cosine theta plus r sine theta times I. And so that's just transferring that a to the r cosine theta and then transferring the b to the r sine theta. So the next slide has the nice little way to write that. And let me see if I have a written on one. I do. Maybe, yeah, I'll leave that one up. So now you're going to write the trigonometric form of a complex number. The trigonometric form of a complex number, z equals a plus bi, is z equals r parentheses cosine theta plus I sine theta, close the parentheses, where a equals r cosine theta and b equals r sine theta and r equals the square root of a squared plus b squared. And the tangent of theta equals b over a. And so just a little clarification, that tangent theta equals b over a is going to give us a reference angle, and then we're going to have to find what the actual angle is in reference to that. And so just some reminders here that a equals r cosine theta, so that's something you want to know. A equals r cosine theta. B equals r sine theta. And then z can be written these ways. Z equals a plus bi. So we can have that as r cosine theta plus r sine theta I. And then just distributing out the r, that's how we get this r parentheses cosine theta plus I sine theta. This is called the trigonometric form of a complex number, is also called the polar form. And these are polar coordinates with r and theta. And if Professor Ouija does come to visit us again, sometimes he comments on the polar form. This book does not say much about that, but when we're doing this trigonometric form of a complex number, that is polar form. And there are an infinite number of choices for theta, so the trigonometric form of a complex number is not unique. So just be aware of that. It's not really going to affect us as we work through our problems. Normally, theta is restricted from 0 to 2 pi, but sometimes we'll use an angle theta that is less than 0. You know, sometimes it's easier just to work down in that fourth quadrant as we do a problem or two. And the other thing is, I did think it was maybe on here, but I don't see it. And that is that, oh yes, it's at the bottom here. R is called the modulus, and theta is called the argument. And I will refer to that later. R is the modulus, and theta is the argument of z, that complex number. So just be aware of that, and you know, if you don't remember that, it's not a super big deal as we go through. So now we want to write a complex number z in trigonometric form. To do that, we have to find r and we have to find theta. And so that's what we're going to kind of look at. So this is number 2, z equals -2 minus 2 the square root of 3i. And you'll notice, you know, and there's a typographical error later. This is the square root of 3 and then I is behind that. And you know I don't like to write it that way, but I do follow that for these numbers as we go. So 2 things we have to find is r and theta are the two values that we have to find. R is the square root of a squared plus b squared, and I'll just remind you this is z equals a plus bi. So a in this case is -2. So this is going to be the square root of -2 in parentheses squared plus, and then b is -2 the square root of 3, -2 the square root of 3 in parentheses squared. And so I'm going to actually erase that theta because I think I need to use my space a little bit. And so that's the square root of 4 plus, and then -2 times -2 is 4. Square root of 3 times square root of 3 is 3. 4 times 3 is 12. So that is the square root of 16. So R is equal to 4 in this case. So that's how we find R, just the square root of a squared plus b squared. And then we also need to figure out what theta is. And so to figure out what theta is, I'm going to draw my little right triangle or excuse me, not my little right triangle, my all students take calculus quadrants. And I'm just going to think to myself, if I was going to plot this AB, that would be -2, -2 square root of 3. And, you know, I don't care exactly where they are, but I want to see what quadrant they're in. So the A is negative and the B is negative. So that means to me that this would be someplace down here, wherever that is. So I'm going to think about the reference theta that is right there. And so to find theta, I'm going to take, or my reference angle, I'm going to take the arc tangent. I'm just going to remind myself, let me back up because I didn't like how I was writing that. I'm going to remind myself that the tangent of theta is b over a. Oops. And so that means to get my reference angle, I'm going to take the arc tangent of b over a, and then consider my quadrant and get my angle from there. And so for my reference angle, I need the arc tangent of, and then b over a is -2 the square root of 3 over -2. And so that is the arc tangent of the square root of 3. And so I'm asking myself for the reference angle, what angle has a tangent of the square root of 3? And kind of think about your table, and tangent is down here, and square root of 3, it's kind of over there someplace. And so the reference angle is pi over 3 for that one. And so my reference angle is pi over 3. And I am going to get rid of that little piece. So that's my reference angle. Then my actual angle, positive x-axis down to here. So there's my actual angle theta. And theta is going to be pi plus pi over 3, or 3 pi over 3 plus pi over 3. So that's going to be 4 pi over 3. And then my job is just to write this in trigonometric form. So the trigonometric form, I'll highlight that in purple, is R, or Z equals, I was going to start with the R, Z equals R, parentheses, cosine theta plus I sine theta. And so my answer for this is Z equals R, which was 4, parentheses, cosine 4 pi over 3 plus I sine 4 pi over 3. And that is the complex form of that. Actually, if I figured out the cosine of 4 pi over 3 and the sine of 4 pi over 3, and then I distributed that 4, I'd just get back to my original problem that's right there. So just kind of letting you know that's what would happen in that situation. So that's how to write the complex number a plus bi in trigonometric form. The next problem I have here is number 3. I have this handwritten. Now, if I have z equals the square root of 8, bracket cosine negative pi over 3 plus I sine negative pi over 3, and I want to write that in a standard form. So this is in trigonometric form. Let me just write that. So this is z equals square root of 8. And by the way, notice that's not in simple radical form yet. Cosine negative pi over 3 plus I sine negative pi over 3. And so this, just a note to self, this is in trigonometric form. Trigonometric form. And we want to change it to standard form. And we'll just remind ourselves that standard form is A plus BI. And so really what we're going to do is just take that, and I'm maybe just going to clone it so I can have it down a little lower. I'm just going to take this and see what I can do to put it in A plus BI form. So first I'm going to start by saying, well, the square root of 8, remember 4 is a perfect square that goes into 8, so that's 4 times 2. So the square root of 8 is 2 the square root of 2. And, you know, you could do that at the beginning or the end or whatever. And then I have to figure out this cosine of negative pi over 3. So I'm going to put a little box here, and I'm just going to remind myself, all students take calculus, and that negative pi over 3 would be down here. And then my reference angle is just pi over 3. And I'm going to need both the cosine and the sine of that. And so as I look at that, and the sine of negative pi over 3 will be negative. And think about where pi over 3 is, and that will be negative square root of 3 over 2. And the cosine of negative pi over 3 is cosine is positive in that fourth quadrant, so that is positive 1/2. So now I'm ready to kind of put that in, and so the cosine of negative pi over 3 I got was 1/2 plus I times the sine of negative pi over 3, which is negative square root of 3 over 2. And so those are multiplied. I'll just write it like that. So then what that means, I'm just going to go this way a little bit. As I distribute that across here, I'm going to just multiply that and that. I'm going to get 2 the square root of 2 to the square root of 2 over 2 plus, and I'm going to put that I in the back, 2 the square root of 2 times negative 3 the square root of, or excuse me, oh, I wrote that wrong. 2 the square root of 2 times negative square root of 3 over 2i. And then on the left one here, the 2's cancel, so I get the square root of 2 plus, let me change that to a minus. Oops. So I get the square root of 2, and then the 2's cancel here. The square root of 2 times negative square root of 3 is minus the square root of 6. So minus square root of 6i. And I am trying to put that I behind there. Make sure that you're careful. And that's what z equals. And this is in standard form. Standard form, which is a plus bi. So we've in the last example, we took something in standard form and put it in trigonometric form, and now we're putting something that was in trigonometric form into standard form. So they're just kind of reverse operations as we look at that. Now, the next thing we're going to look at is multiplication of complex numbers. And so when we do these problems, if we were in class and had time, I'd go through and look at some things. This is the problem that I have set up for us to do, but I'm just going to go to the next slide where I have it worked out. Just a reminder, do you remember this sine of u plus v, and is sine u cosine v plus cosine u sine v, and those little sum and difference formulas. So if we have these two things, z1 and z2, and they are written in trigonometric form, we want to be able to multiply those and kind of come up with a general answer. And so I'm just going to show you my work from another year. So when I'm multiplying those two, I multiplied the R1 and R2 out in front and then just left them out there the rest of the time. So there they are, just moved to the front. And then I just FOILed that all out. So I got cosine theta 1, cosine theta 2, plus I sine theta 2 cosine theta 1, plus I sine theta 1 cosine theta 2, minus the sine theta 1 cosine or sine theta 2. And the reason this is a minus right here is when I do these last terms, I times I is I squared, so it would be plus I squared, but I squared is -1, and so that's how we get that kind of negative in there. Let me get rid of some of that yellow. And then we combine like terms, so this I sine theta 2 cosine theta 1 is the same as I, or excuse me, oh, is not. Never mind. I was just doing the wrong thing there. I just have these arrows here. I just changed the order there. And then look at what is written in black here, that we get cosine cosine minus sine sine. And hopefully you recognize that as cosine cosine minus sine sine is cosine of u plus v, and in this case cosine of theta 1 plus theta 2. And then likewise in green, I think it is over here, we get that sine cosine plus cosine sine, and that's this version, which is the sine of u plus v. And so we get the sine of theta 1 plus theta 2 for that one. So I just wanted you to see that, because look at what this result is then. It says when we multiply those two complex numbers in trigonometric form, we can just multiply the R1 times R2, and then it's going to be the cosine of the sum of those angles plus I, the sine of the sum of those two angles. And so if you remember, I called R the modulus. So when you multiply these, you're going to multiply the modulus, and you're going to, theta is the argument, and then you're going to add the argument. So multiply the modulus and add the argument is kind of the way we can say that. And so then I just did want to go over that. Then we'll go, you know, if we had time, we do the division problem. This is now the multiplication and division of complex numbers. And so I don't have to go through those couple slides. I just read through that with you. And then here's what you want to write down. This is the product and quotient of two complex numbers. So if Z1 is A plus BI and Z2 is C plus DI, then we can turn those into trigonometric form first, and then Z1 equals R1 cosine theta 1 plus I sine theta 1, and Z2 equals R2 cosine theta 2 plus I sine theta 2. Be careful that you're subscripting and not superscripting, because they're not squared or anything. And those are our complex numbers. Then Z1 times Z2 is R1 times R2, and then usually we're going to put a bracket, cosine parentheses theta 1 plus theta 2, close the parentheses, plus I sine parentheses theta 1 plus theta 2, close parentheses, bracket. And then when we divide the modulus and we subtract the argument. And so if we're going to divide these two, we're just going to divide those and then subtract. So multiply is multiply and add, divide is divide and subtract, and the modulus and the argument. So when we're multiplying, we multiply the modulus and add the argument. When we divide the modulus and subtract the argument. And so if you need a moment to write all that down, I'm going to get rid of some of this yellow, and then we'll move on to the next problem. So I'll move on and you can do whatever you need. And that just says what I went through. Then, so here's example 4. These are written in trigonometric form, and we're going to find that product. And I'll just rewrite it because I know that'll be giving you time to rewrite it. So z1 equals 3 parentheses cosine pi over 4 plus I sine pi over 4. And z2 is equal to 2 parentheses cosine 3 pi over 4 plus I sine 3 pi over 4. So then our job is to find z1 times z2. And so we're just going to multiply 3 times 2. And that's from these two, just that 3 times that 2. And then we'll put a bracket, and it'll be the cosine parentheses, and then we'll go pi over 4 plus 3 pi over 4. And the two things that we're adding here are this and this. And notice they're going to be the same pair for sine when we match those together. So then we're going to say plus I sine parentheses pi over 4 plus 3 pi over 4. And then close that bracket. And then we're just going to kind of work things out, and we're going to get it in that standard form a plus bi in the end. And sometimes you're going to find that a few of these examples, either this turns out to be a real number or possibly a pure imaginary number, and sometimes it'll just be still complex a plus bi, but just be aware of that. So 3 times 2 is 6, and then cosine pi over 4 plus 3 pi over 4 is 4 pi over 4, or just pi. So cosine pi plus I sine pi. And I could have changed that to parentheses already, but I did not. And then we have 6. So then when you think about the cosine of pi, maybe I'll use a different color, just a second. And when we think of the cosine of pi, pi would be over here. And if you put a point there, that would be maybe -1, 0. And that's kind of cosine, sine, cosine theta, sine theta. And so the cosine of pi is -1, and the sine of pi is 0. So that gives us equal to 6. I don't have to write cosine anymore. Cosine of pi, which is times -1, and then plus I, and then sine of pi, which is 0. And so then when we figure that out, that is 6 times -1. So that is just -6. So z1 times z2 is just equal to -6. So that turned out to have a real answer as we looked at that one. So we'll look at another one of these as well, and then we'll move on to kind of the next thing. So here's the next one. Find the product of z1, z2 of the complex numbers. So I'm just going to pause like a few seconds here, and I'm just going to state that if you need a few more seconds or whatever, or if you want to try this one yourself, maybe you want to pause this to write it down, pause it and try it, and then you'll see me work it out. Okay, so now either pause it or I'm going to go right through this. So z1, z2 is going to equal the product of the modulus of each of those. And so that's going to be 2 times 8. And then it's going to be the cosine of the arguments, this and that, added together, the sum of the arguments. And so that's going to be cosine parentheses 2 pi over 3 plus 11 pi over 6, and then plus I sine, my S didn't come out very well, 2 pi over 3 plus 11 pi over 6. And so then I have to do some work with that, get a common denominator, add those, and just see what happens here. So 2 times 8 is 16, and then cosine, and I'm just going to do a little work right here. So to get the common denominator, I'm going to multiply that by 2 over 2. So I have 4 pi over 6 plus 11 pi over 6, and that's 15 pi over 6, and then 15 pi over 6. Well, maybe I will write it that way. Cosine 15 pi over 6 plus I sine 15 pi over 6. And then I'm going to just leave my 16 for a minute. And then I'm going to reduce that. 3 goes into each of those. So that'll be cosine 15 divided by 3 is 5. Pi over 6 divided by 3 is 2. Plus I sine 5 pi over 2. And then I'm going to do that same old, here's my coordinate axis. I have 5 pi over 2. And so if I kind of think about counting around, this is 1, 2, 3, 4, 5 pi over 2 puts me right there. And so if I call that point 0, 1, that's cosine comma sine. And so then that means the cosine is going to be 0 this time, and the sine is going to be 1. Let me get rid of that. I forgot my bracket there. So this means this is going to be 16 times 0 plus I times 1. And so that is going to be 16I for Z1 times Z2. And so that one ended up to be kind of a pure imaginary number, A plus BI, as we look at that. And I'll just show this slide next, or just a second after. I thought I had a slide. Maybe I got rid of it. That you can, you could check that by taking those two things and multiplying them. You can check that by putting those original Z1, Z2 into the standard form, A plus BI, multiplying them and seeing if you got that same result. Just to kind of let you know is another way to do that. Number 6 is a quotient problem. And so I'll again tell you, if you want to try this yourself, it's just this dividing the modulus, subtracting this time the argument. And so if you want to do that, you sure can. And if not, you can just keep following this. If you need to write it down, go ahead. And I'm just going to move on. So to find Z1 divided by Z2, we're going to take the quotient of these two numbers. So 24 divided by 8. And so then I'll write that, 24 divided by 8, then bracket cosine, and this time we're going to take these two angles and subtract those. So 300, it's going to be minus 75, and I'll just write that in here. And this is in degrees this time, so 300 degrees minus 75 degrees, and then plus I sine, same thing, 300 degrees minus 75 degrees. And then we just kind of work our arithmetic and things that we know. 24 divided by 8 is 3. This is cosine 300 minus 75 is 225 degrees, plus I sine 225 degrees. And then we're going to put this in standard form again. So my next job is just to take this version of that, and I'll move that down if you still need to see that. And kind of think over here. I've got 225 degrees, so we don't work in degrees a whole lot, but I'm at 0, 90, 180. Down here would be 270, so it's someplace in there. And so all students take calculus. So tangent is positive. Both cosine and sine are going to be negative. And my reference angle for this one is 225. My reference angle is 225 minus 180. So my reference angle is 45 degrees as we look in degrees. And so my cosine is negative, my sine is negative, my reference angle is 45, so those are square root of 2's over 2's. So the cosine of 225 degrees is negative square root of 2 over 2, and the sine of 225 degrees is also negative square root of 2 over 2. So then I'm going to go back up to my problem here, and I'm going to say, let me just kind of put a little circle around that. This is equal to 3, and then times the cosine of 225, which is negative square root of 2 over 2, plus I, and then the sine of that is negative square root of 2 over 2 also. And then I'm going to distribute my 3, and so this is equal to negative 3 the square root of 2 over 2. And then when I distribute and multiply, and I'm going to put the I in the back now, but 3 times this negative square root of 2 over 2 is minus 3 the square root of 2 over 2. And then I'm sitting my I kind of in the middle of that fraction part. So that is finding the product and the quotient of these in trigonometric form. And so the next thing we're going to do is look at powers of complex numbers. And so let me just go to this slide. If you need to write that down, go ahead. And then I'm going to move on. And so this just illustrates, and I'll let you look at that. So if we're going to take z equals r cosine theta plus I sine theta, and instead of taking z1 times z2, we're just going to take z times z. And then notice that that's going to be r squared times the cosine of 2 theta. And then if we did it r to the third, just multiplying by itself again, that r cosine theta plus I sine theta, then if z to the third would be r to the third cosine 3 theta. And so then in general, you don't have to write this yet because it'll be on the next slide. If I have z to the n power, then that's going to be r to the n power, and then the cosine of n times theta plus I sine n times theta. And let me get rid of that yellow stuff just to move on. And so this is called de Moivre's theorem, and DEMOIVRES apostrophe S theorem. And de Moivre's theorem, so you want to write this down, of course named after a French mathematician, Abraham de Moivre. And de Moivre's theorem says if z equals r parentheses cosine theta plus I sine theta is a complex number, and I'll add in trigonometric form, and n is a positive integer, then z to the n equals bracket r parentheses cosine theta plus I sine theta parentheses bracket to the n. And that's not our most interesting form. Our interesting form is this version down at the bottom. So z to the n is equal to r to the n cosine n theta plus I sine n theta. And so you want to make sure you write that down, and you want to know de Moivre's theorem. Now, the next problem is number 7. And one thing I want to say about this problem is notice this is written in standard form and it's taken to the 12th power. Now, if you truly wanted to, you could sit there and go 1 plus the square root of 3i. Oh, by the way, I forgot to tell you that there's a little error on this slide and I was going to fix it, but then I forgot. Let me just kind of get a little white box here and this is just the square root of 3. I is not under that radical. So if you wanted to really sit there and go parentheses -1 plus the square root of 3 and then I, and then times that by itself 12 times, you could get this answer that way. But when it's written in standard form, the first thing you want to do is really, it's to your benefit to change that into trigonometric form and then use de Moivre's theorem to find what that answer is. So this is a two-part problem, and this is numbered as 7a, and it says use de Moivre's theorem to find -1 plus the square root of 3, and then that I is offset raised to the 12th. And I'm going to give you a two-part directive. This is two parts. Part 1 is to convert into trigonometric form, convert into trigonometric form. And then part 2 is going to be, to use de Moivre's theorem. De Moivre's is what is actually in my head. Oh, I shouldn't even try to cursively write that. So, and I'll kind of color code these as well. So part 1, and this is a good review of the beginning of this lesson, but part 1 is just to take this, part 1 is to take this -1 plus the square root of 3i, and that is a plus bi. So that means a is -1, b is the square root of 3, and we're going to write that in trigonometric form. And so r is the square root of a squared plus b squared, so -1 squared plus the square root of 3 squared, not including that I, just keep that in mind. So r is the square root of 1 plus 3, r is the square root of 4, so r is a plane 2. So that was pretty straightforward. And then to figure out what that theta is, this is finding r and theta, to figure out what theta is, kind of think about where that point is. So if it's negative, a is negative and b is positive, it's going to be someplace maybe up there. And so all students take calculus. Our angle is right there. And to get our reference angle, we use the fact that the tangent of theta is equal to b over a. And so the tangent of theta is the square root of 3 over -1. And so the tangent of theta is negative square root of 3. Think about your chart for the trig functions, and if you're at the square root of 3 for tangent, the reference angle is pi over 3. Is reference angle equals pi over 3. And so then if my reference angle, which I'll put in yellow, my reference angle is right there is pi over 3, then the angle that I actually need is this angle right here. So that's 1 pi over 3. So this angle is 2 pi over 3. So theta is 2 pi over 3. And so then this in trigonometric form, I'll just name it z then. We can say z equals 2 parentheses cosine 2 pi over 3 plus I sine 2 pi over 3. So that is part one. Part one is just to take whatever that a plus bi is, which is in standard form, and change it into trigonometric form. Now, part two, and I'll just start it right here. Part two is now to use de Moivre's theorem. And so that is now going to be finding z to the 12th, because I just named that z a minute ago. So z to the 12th is going to equal, and I'll write it first this way, as a bracket, 2 parentheses, cosine 2 pi over 3 plus I sine 2 pi over 3 in parentheses, bracket to the 12th. So that's what I'm finding. All I did so far is change that standard form complex number into a trigonometric form. And now I'm just going to use de Moivre's theorem as I go. So the 2 here is my modulus. So I'm going to take 2 to the 12th. That's where I'm going to get these parts. And then I'm going to take, for my angle, this 2 to the square root of 3 times 12. And that's how I'm going to use de Moivre's theorem for this problem. So when I write this then, I'm going to say this is 2 to the 12th bracket cosine of 12 times 2 pi over 3 plus I sine 12 times 2 pi over 3. And so the 12 is no longer in that top right corner. I've kind of distributed through the problem, and so I just kind of keep working from here. 2 to the 12th, just use your calculator for that. That is 4096. And then this is going to be cosine, and let's see, 12 thirds is 4, 4 times 2 is 8. So this is cosine of 8 pi plus I sine 8 pi. And then I'm going to put that back into standard form. And so I have to handle this cosine of 8 pi and kind of think about where that is. I don't know, I've run out of room to the left, so I'm going to move to the right, and I'll just put a little box here or something to kind of think about that. So 8 pi, I'm at 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. So really I spun 4 times, and I should have known that. And so my point is that I can pick as 1, 0, and that's cosine theta, sine theta. And so then I can just put those in my problem here. And so I'm going to have 4096 bracket, and then cosine 8 pi is going to be 1. Plus I, and sine 8 pi is 0. And so a little color coding there. And then, well, 0i is just 0 and 1 is 1. So 4096 times 1 is 4096. And in this case, z to the 12th turned out to be a real number. And it may or may not turn out to be that way as we go through these problems. So those are good ones for you to practice. I think that's enough, and I took 52 minutes and 26 seconds so far, so this is certainly enough for you to go over. The next part of this, oh, I have another one for you to do. Well, let me see. There's another one. Let me go back. Okay, so I just flashed the answer there. But here's the next one. Maybe you want to try that one, and I'll leave that for you to try. And so if you want to pause this right now and try it, and then I'm just going to show the answer because you've probably heard enough from me. And if you want me to go over it on Monday or Tuesday, I sure can do that. Oops. So hopefully you have paused this, figure it out, and then I'm going to show the answer. Here is the answer for like really the third time, but then I'll leave it there. So part one, and it's kind of a little messy, is to find R, and I did that, and then find the angle theta. So I'll step through this a little bit because I do see it. It's kind of awkward looking. So part one is right there. Square R is the square root of 2. When you plot that point, it's a negative and a negative. So it's in that third quadrant. It's the tangent of theta is 1 over 1. So the reference angle is pi over 4. And then the actual angle, since that is pi over 4, 4 pi over 4 plus 1 is 5 pi over 4. So there's theta. So here's that trigonometric form. Square root of 2, parentheses, cosine 5 pi over 4 plus I sine 5 pi over 4. And then that's raised to the 4th power. And it looks like I had a unique green there, but I'll just put that bracket a little better. It looks like a mess there. And then it looks like we take the square root of 2 raised to the 4th. And notice I turned that into a fraction. So that's 2 to the 1/2 times 4. So that's 2 squared. And that's just going to be plain old 4. And then I take, it's a little hard for me to even read myself, but that's 4 times 5 pi over 4 because we're raising this to the 4th power. And that turns out to be 5 pi. And here's where 5 pi ends up. And cosine of 5 pi is -1. Sine of 5 pi is 0. So we get the -1 there. We get the 0 there. And that one turns out to be -4. And then now I'm to roots of complex numbers, and I will, again, on Monday, I'm going to finish 6-4. If you want me to finish 6-5, I will, or if you want me to wait till Tuesday, whichever way you want to do that, I'm pretty confident that I can get the rest of that done in a class period. But if you want me just to go through it on Monday and then you have Tuesday to work, and then Wednesday morning will be a help session, Wednesday test, Thursday no class, and then Friday test. So have a great weekend. This has been almost an hour, and I hope you are enjoying yourself. See you on Monday.